1.10, we are discussing scatterplot. So yesterday we were making and interpreting graphs. Scatterplot is just another graph just filled with a bunch of dots. For this section, we will be using Desmos. So make sure that you have the little green Desmos icon downloaded onto your iPad because I'm going to go through how to use Desmos for this unit and a couple questions later. This section has a lot of writing, so I actually left all of the writing here so I'm not wasting time rewriting all of the answers for you as we go through them, but I will go through each and every one of these first 5 problems with you. Okay, so this is a graph showing high school GPAs and SAT scores for students who applied at a particular university. Each dot represents a student and is color-coded to indicate the student's admission level. So accepted but won't be attending college, waitlisted, accepted, and denied. So the first question, what do the blue dots represent and where do they seem to be clustered on the graph? Explain why that makes sense. So the blue dots are those who have been denied, and they are pretty much clustered, I would say, right here. Kind of on the left-hand side of the graph. So left-hand side of the graph means a lower SAT score. So these students were denied because they have a lower SAT score. If we're looking in particular, I would say big cluster right here. And that also indicates a somewhat lower GPA. It looks like most students have between a 3 and a 4 GPA. A couple of these students have a 2.8 to a 3.2 GPA. But the biggest indicator for them being denied is this low SAT score. Question B, what do the green and purple dots represent and where do they seem to be clustered on the graph? Explain why that makes sense. Are there any green or purple dots that seem to contradict the trend? So I'll erase this. So green and purple dots. So accepted but won't be attending and accepted. So green and purple are pretty much clustered right here. So all of these students were accepted. Whether or not they decided to attend the college or not, they all got accepted. And they all had about, 1,700 SAT score. So they had a higher SAT score and pretty much all of their GPAs were a 3.0 or above. Now, are there any dots that seem to contradict the trend? That would be this dot and maybe those 2 dots. They were accepted. This particular student had a very low SAT score and a pretty average GPA. And these 2 students had 1,500 SAT score and a high GPA. So why do they kind of fall outside of our main cluster? Not all colleges base their acceptance just on SAT and GPA. Some colleges will look at your admissions essay, or they might look at extracurricular activities and take that into consideration when making a decision whether to accept or deny a student. So just because you have a low SAT score doesn't mean that you're necessarily written out from college. And then part C, notice that there are blue and orange dots representing students who were waitlisted or denied admission behind some of the green and purple dots. Explain what that means. So we have, looking here, we have a student that was accepted, and then we also have students that were waitlisted, and they all seem to be, they all have pretty much the same data. So why were these students denied even though their test scores were as high as others that were being admitted? Again, schools are looking at other criteria outside of SAT and GPA. So interviews, letters of recommendation, extracurricular activities, that college admissions essay, all go into factoring whether you're admitted, denied, waitlisted, accepted. All right. That was fun, wasn't it? Get us thinking about colleges. Okay, so independent, dependent variables. This was literally the first thing that you learned in Math 1. Independent and dependent variables. Remember, dependent depends on the independent. Independent can stand on its own. Dependent, I don't want to say the word depends on again, but yeah, it depends on the independent. So if you think about an adult and a child, an adult is independent. They can usually and should be able to take care of themselves. They're able to dress themselves, feed themselves, get themselves to work, pay their bills, what have you. The dependent would be the child. They rely solely on that independent adult in their lives. Younger children cannot feed themselves, dress themselves. They are totally relying on somebody else to do that for them. So, thinking in math terms, if you are going 60 miles per hour, you're traveling for 1 hour, then you go 60 miles. If you travel for 2 hours, then you will go 120 miles. In this sense, your distance depends on the time. Time is not passing because you're driving. You're not going to go, okay, well, I'm going to drive 60 miles, so that means time is going to go 1 hour. Doesn't make sense. It sounds silly even trying to explain it. A little bit more about scaling a graph, increments, all that. An example here for a scatter plot. This first column usually represents the independent variable. The second column usually represents the dependent column if it's set up correctly. So from there, they kind of help you with this chart here on everything about the x values, everything about the independent variable. Independent is always x values, dependent is always y values. So things to look for is your minimum value, your maximum value, and then from there, you can kind of scale your graph. So for GDP per capita, you can kind of think of that as salary, like an individual salary is just in layman's terms how I would explain that. If you're taking like econ, and I know that was a very basic definition. If you're taking econ and you're like, wow, Ms. Sanchez, you really have no idea, you're correct. I don't. So minimum value is 0, meaning somebody earns $0 per year, all the way up to the maximum value of $60,000 per year. Yes, I realize people make more than $60,000, but we're just going with it. So in this case, we are going to scale our graph by 50,000 or 5,000. Just because I'm scaling it by 5,000 does not mean that I'm writing down each 5,000 increment. We can represent every other with a little tick mark there. So really, we only wrote every 10,000 value. And then for social media, percent using social media, the minimum value was 0%, maximum value was 60%. So in this case, we're going to scale by 5s. And again, we represented a little dash or a tick, and then we have 10 dash, 20 dash, 30 dash, so on and so forth, okay? We labeled our axes, and then we just graphed these as a coordinate, x, comma, y. Okay, super tedious work, I know. But from there, you can kind of interpret the graph, okay? Pakistan, India have a low yearly income per person, and so they're not really on social media a lot. The United States, Great Britain, Germany, we'll throw Japan in there too, have a higher GDP, a higher income per year, and they're using social media a lot more. Israel might be considered a little bit of an outlier. They're using a lot of social media, but their income per year is pretty much smack dab in the middle. Ukraine, China, Egypt, pretty low income per year, kind of low on social media trends. Okay. that's enough about that. Let's actually go through an example ourselves. So this is a scatter plot showing salary and years of experience. Usually the longer you've been an employee at a company, the more money that you'll make because you have more experience. So 0 years, your starting salary is $48,000. If you stay with that company for 23 years, your income or your salary will go to $92,000 per year. Fabulous. Okay, so I know that this is going horizontally, but time is independent. So these are our X values. These are our Y values. Your salary depends on your years of experience. Okay. So we're looking at independent variable. Those are our X values, our time, years of experience. It is on the horizontal axis because they are X values. We go from 0, and I'm just going to round this to 25 just to keep it nice, and then I can use increments of 5, 10, 15, 20, 25. Pretty nice and easy. And then the dependent variable, salaries depending on your experience, it'll go on the y-axis or the vertical axis. Our minimum salary, again, I just rounded to an even number, which was 40,000, and then my maximum value I rounded again to 100,000. You can keep it specific if you would like, but to make my increments at 10,000, I thought that was nice and easy. So then from there, this is so tedious to make, I realize. So that's why I created it once and just threw it into my video. So I have my salary from 40,000 to 100,000. My years of experience from 5 to 25. I put this little Z in here to indicate that the jump from 0, which is right here, 0 to $40,000 is not an equal increment as right here. So there's a break in my graph. That's why that's there. And then I put the dots. And as you can see, the more years you work, the more experience you have, the higher your salary goes in a pretty consistent, I would say, linear pattern here, if I drew a line through the middle. And then what conclusions can be reached from this scatter plot? I just said salaries tend to increase as your experience increases. So we're going to actually make a scatter plot. It says here to use a graphing calculator. I hate graphing calculators so much. So we are actually going to be using Desmos for this to create our scatter plot. And I'll show you just with this one because it has nice small numbers. So I'm going to open up Desmos. I can just have it hover on the screen here, or you can pull it up. I can never get it to work, so just leave it like that. Okay, we're going to hit this plus button right here, plus, and then we're going to go table because I want to recreate this table. So I have my X values and my Y values, and I'm just going to plug in 2, 4, 7, 10, 14, and then college GPA is my Y value. I'm going to go 1.8, 2.2, 2.4, 3.2, 3.8. And then I can see if I zoom in and out, I can zoom out really far, I can zoom in further. All of my points are there. The scatter plot was created for me. Super easy, super nice. Love Desmos. Okay. That's enough of that. For each of the following scatter plots, sketch a smooth curve through the points to indicate the model you would indicate, or you think the data points seem to follow. So this is your line of best fit. The line or curve should look like it passes through the center of the cloud of points. It does not necessarily need to go through each point or any points on the graph. So I just threw in my lines of best fit into these. Shouldn't be anything too difficult. This one was a nice little curve here. Yeah, hopefully that wasn't hard. Question number 4. Match each description to the graph you think best illustrates it. Identify the independent and dependent variables for each case. So independent variables for our x values, dependent was our y values. So the x-axis would be independent, dependent would be on the y-axis. So you save the same amount of money each month in a non-interest bearing account until you reach your goal. Then you just leave the account at that balance. So time is always independent, and we are measuring it in months. And what happens each month? Your account balance changes. So I said that goes with graph VI, so 6. So we added interest, and then we just left it and just kept it consistent, that same balance. We kept the balance consistent. Number 2, average monthly temperatures at a given location. Again, time, months, always independent. What happens every month? Temperature. Okay, I said that goes with graph number 5 because this one was a little bit difficult. I said this was out of an entire year. So in the summer months, it is hotter. In the winter months, it is colder, and then kind of evens out in the spring and fall. Part C, population of bacteria doubles every hour. Again, there's our time, so time in hours, what's happening every hour, population of the bacteria, and it's doubling, so that goes with graph number 3 because we are exponentially going up. Okay, doubling is exponential. That's an exponential graph. D, the height of a ball each second after it's shot from a catapult. Okay, again, seconds, that's time. What's happening? The height of the ball being shot from a catapult. So what did I say that one with? Graph I, so here's our catapult. The ball is shot out, goes up, and then it goes down. That drawing was terrible. I was trying to draw a cannon. Okay. Yeah, that's good enough. Okay. E, the number of days needed to build a bridge compared to the number of workers. Okay, this one, a little bit tricky. It's actually the number of workers and the time in days. Time in days depends on the number of workers. So I know that I said time is always independent. In this case, it is not. The more workers you have, the less time it takes to build this bridge. If you only have one worker building this bridge, it's going to take a lifetime to build. If you have 1,000 workers working on this bridge, it'll probably just take a couple days. So I said that this went with graph number 4. If we had one worker, it's going to take us like 300 days. This is workers. Okay. If I had 300, maybe it just takes us 10 days. Okay. If I had 5 workers, it'll take us 30 days or something like that. Okay. And then the last one, number of students at a college campus who contract a highly contagious flu virus. Oh, they predicted the coronavirus in this book. Okay. Time in days. Number of students being infected is dependent. So it starts out if you look at any coronavirus trend, this is kind of what you'll see. This is kind of where we're at right now. It starts out slow. This was like our time in March, and then it increases kind of quickly before leveling off, and that's kind of where we are right now. I know that the coronavirus kind of went back down and then up, and hot mess, but we have one more. Okay, number 5. Ratio of elderly people number of elderly people to working age people in the United States has increased for many years. This is potentially serious problem since working people tend to pay taxes that support services for the elderly. The ratio of elderly people to working people is affected by increasing longevity and decreasing birth rate. So people are living longer and dying less at birth. So consider the following scatter plots that shows the number of kids per woman versus the number of elderly people per 100 working age adults for various countries in 1960 to 2015. The orange dot represents the the United States? Again, I wrote in my answers because they are long and I don't want to write them. So how did the United States compare to other countries shown in the 1960s? So United States right here. United States had, I don't know, like 18 elderly people working per 100 working adults. So we had a lot of elderly people per working people. And then we didn't have too many kids per woman, about 3 kids per woman. Most other countries, I would say, are scattered up here. They have less elderly people and more children per women. So we had more children and less elderly people, okay? That's kind of what I wrote there with a little bit more specific on the numbers. How did these measures change for the United States in 2015? So 2015, here's our little United States dot. How do we compare? Well, the number of elderly working people per 100 working aged people, so the number of old people has increased to about 25 now versus that 17.5, 18, which is closer to the average of the other countries. We're kind of smack dab in the middle. We have also lowered the number of kids from 3 to 2, and we also notice that other countries have lowered their number of children. Describe the changes in the scatter plot from 1960 to 2015. Okay, so we've noticed that, let me erase this so I can redraw on here. Notice that we had a lot of kids, not too many working, or I drew that backwards, not too many elderly people compared to the number of people that are working. So a lot of kids, not too many adults, elderly, I should say. And then in 2015, our graph kind of like fell down. We have more elderly people and less children being born per woman. And that is it.